Thanks, everybody. So I want to tell you guys about our journey at Nike to realizing DevOps for data science, some of the pitfalls we encountered, some of the patterns that changed to enable data science to deliver their own code into production and own the entire life cycle of that code base. So a little bit about our team at Nike and what we do. I'm on the personalization engineering team. We power Nike experiences with machine learning recommendations. So that could be in the .com webpage. We recommend products on the product display pages, recommend products or search terms. In the apps, we also do product recommendations or workout recommendations. So we're the point at which these digital experiences integrate to be powered with machine learning recommendations. We do that through this product recommender service. This is the layer where the A/B testing happens. We maintain product meta information to ensure we're not recommending products that are out of stock. We want to ensure that users can actually purchase these products. We also own the model serving layer for machine learning models, whether it's batch collaborative filtering models, where we need to index the big batch machine learning recommendations into something we can serve to users, or our real-time model serving layer, which would deploy and serve TensorFlow save models in Kubernetes containers. So we'll own that serving layer as well. Additionally, we were tasked with productionizing the models and doing model operations for machine learning models delivered by data science. So generally what that consisted of was build the Airflow execution pipeline for that modeling code, maintain and monitor that code in production to resolve any processing failures so that we can serve fresh recommendations to our consumers. And this is what we noticed was our primary bottleneck in delivering machine learning models into production. It would take a long time. And it wasn't necessarily because it was a complicated thing to do, but it required a ton of coordination from the data science team and the engineering operations team. We might have the model code base delivered to us with instructions on how to execute it, what the cluster resources were. Often there would be artifacts missing from that, or when we went to productionize it, we would execute code paths that weren't necessarily covered in development time. So if there was a failure, we had to do our due diligence to try to fix it and then bring it back to the machine learning data science team to try to resolve it, and the cycle could continue. So it could take anywhere from 3 days to worst case scenario. I think it took us 3 months one time to productionize a machine learning model. This was the primary constraint and bottleneck in bringing new machine learning models into production and the topic of this discussion. So what we cover is why should we do DevOps and data science, what the benefits of DevOps and data science are, how you can adopt DevOps and data science. That includes automate and simplify the data processing pipeline, add observability to your code so you know what it's doing in production. You can observe and monitor that execution and hopefully resolve issues before they manifest in failures. And we can generalize the CI/CD pipeline. We shouldn't have to write a CI/CD pipeline every time for any machine learning pipeline or ETL data job. So this covers the generalized data processing use case, whether it's an ETL job, whether you're creating and publishing reports, whether you're training a machine learning model, creating a batch set of recommendations, a real-time model. Any data processing can be covered with this tool set and in this use case. Another way to look at it is anything you could do on Databricks or EMR, you could cover with these tools. It doesn't necessarily cover the serving infrastructure. Usually your model serving infrastructure is going to be very specific to your use case. There might be latency requirements, real-time versus batch and whatnot, and it's hard to generalize that model serving infrastructure use case, but we can generalize the data processing use case and automate around it. So why should you do DevOps and data science? We wanted to deliver machine learning models to Nike experiences faster. We wanted a higher level of quality in those machine learning models. More importantly, we wanted to lower the threshold for doing an A/B test. Once a model's out there, we have the ability to do A/B testing, but it's hard to justify the small ROI you might get in the A/B test for the cost it takes to bring a new model into production. So we wanted to lower that threshold as much as possible, enable data scientists to start doing their own A/B testing on their models so that they could refine them and improve those models. We wanted code in development to run the exact same way as it does in production. We wanted any processing failures to quickly be identified and resolved. We wanted to break down the silos and kind of the throw it over the wall syndrome. And this really impacts how the teams work together. With the code kind of being handed off, there wasn't a sense of ownership with the code, and it could cause a lot of friction between the teams with this sort of shared code base where people weren't necessarily sure what they were responsible for, what that individual or team owned. So this removed a lot of the friction between the teams. So why should you do DevOps and data science? We know the benefits of doing DevOps in web services are obvious, and that's the status quo now. For a web service company to be competitive, they will be practicing DevOps for web services. Similarly, I think that data-driven companies practicing DevOps and data science will have a competitive advantage over companies that don't. The pattern of the operations team and the data science team might work for the status quo right now, but it won't scale as companies start adding more data-driven products and more machine learning in the future. So why aren't we doing DevOps and data science right now? DevOps isn't a new concept. We've been doing it in web services for a while, and we know the benefits of it, and there's a lot of patterns and automation around it. Early on, this is anecdotal, but my experience, it seems the ETL and analytics side, the engineers writing the ETL jobs, had enough expertise to do the productionization of those ETL jobs as well. Once data scientists started writing models, the expertise to develop a model diverged far enough from the expertise to productionize a model, so that required the operations team to do that support. Someone with a PhD in math or statistics probably didn't want to write an Airflow pipeline and definitely didn't want to be on call for all of the failures that happened once that code was in production. But we can simplify the tool set enough to make it so that any data scientist can productionize their own models and only get notified when there's an issue with their code. They're the person who is capable of fixing that issue in their code, and they should be notified when that happens. Other issues about instances not available, memory constraints, whatnot, those should go to a production support team so that we're not burdening data scientists with that. So the reason we can make these tool sets easier than doing DevOps and data science, or excuse me, DevOps in web services, is all of these data pipelines follow a common pattern. You read some data, you process the data on a resource, a cluster, and you write some data. And you might do that in a number of steps within that data pipeline, but they all follow that same pattern. And maybe at the beginning of that pipeline, you have some task dependencies on other jobs or S3 or some data being available. Every data processing job we have at Nike either fits that pattern or could fit that pattern, and we can automate the tools around that pattern to make it easy for data scientists to bring their own code into production. So what does data science, or what does DevOps and data science look like? It's similar to DevOps and web services. You need tools and automation to get your code into production and easily make changes to that code in production. And you need the ability to observe at runtime what that code is doing. So we do the same thing for data science. We create tools to automatically push their code to production, and we add metrics to the model execution code itself. There's metrics common to all models like processing time, failures, retries, et cetera. And then there's metrics specific to the modeling code like model accuracy, number of records trained on, and whatnot. So you can create metrics around those within your modeling code itself. We need to add SLA and monitoring for alarms and failures. So if your code fails in production, somebody should be notified, and depending on the importance of that job, there should be a service level agreement associated with it, because other people might be depending on that data, and we don't want that failure to quickly cascade. So we can generalize the data processing use case to do all of these things in an automated way. The first thing we needed to do was automate the processing pipeline. That was the biggest point of difficulty in productionizing a machine learning model. The data processing pipeline could only be represented by code, and in our case, Python Airflow code. Not terribly complex to write, but not something that data scientists necessarily wanted to do. So we needed to simplify this data processing pipeline. So our solution to simplify it was to require that every step within this data processing pipeline is parameterless. So what that means is generally in your data processing pipeline, the code would call one step or a Spark task or a TensorFlow task, pass it some specific parameters, call the next step, and maybe pass an output parameter from that first step to the next step. But you had a lot of state in this data processing pipeline. With that state, it's difficult to simplify it or represent it as configuration. So with the parameterless steps, we can now represent those data processing pipelines with simple configuration instead of specific code for the executor. So this is what the processing pipeline looks like now. On the left there, we have our Airflow pipeline, kind of common amount of code there. And on the right, with the parameterless steps, we can now represent the pipeline just with configuration. So in the configuration pipeline, on the left there is the name of the step in the pipeline, and on the right is the step it depends on. So you implement that small amount of configuration, and now you defined what your processing pipeline looks like. So that is easy enough for data scientists to implement. And now that it's configuration, and more importantly, any system can execute this pipeline because it's simple configuration. Jenkins could execute it. You can execute it from the command line. You can execute it from Airflow. You could execute it on Databricks. It's trivial to go and execute the pipeline because it's represented by configuration instead of code that's specific to the scheduler. So steps are parameterless, and normally we pass these parameters from the scheduler. So there needs to be a mechanism to pass information between the steps when the pipeline goes to execute. So the way we do that is we embed a library with the step processing code, like a Spark execution. This is similar to how MLflow does it. So if you're familiar with MLflow, this follows a similar pattern. The one distinction in this from MLflow is MLflow captures the output or the meta information from every execution. This will also provide that meta information into the current execution at runtime. So that allows you to pass information when the pipeline is executing between the steps without requiring you do it in the scheduler or the pipeline execution. I'll dive into how that works in a little bit. But this is just a quick example of in the code what you do. When you start your step, you specify what other steps you depend on, and the output of those steps are provided to this step at execution time for you to reference. So you can get input-output paths, parameters, metrics, anything that was generated by the step you depend on is now available at execution time for this step. So you can reference I/O paths or parameters and whatnot. So that's done through a mechanism we call dependency resolution. So this might be a somewhat common ML pipeline. You run 2 steps in parallel. It could be some normalization or featurization, train a model, score a model, post-process. Each one of these steps will specify in the code what they depend on. And the way these dependencies are resolved is if you were to run 1 and 2, 3, 4, 5, 5 would be provided the most recent executions of all of the upstream steps. If you were to run 1, 2, 3, 4, and then 2 again, and then ran 5, that second execution of 2 would be discarded because we need to ensure that all of the dependencies have a common ancestor or common graph. So if you generated your label data for a machine learning model in the first step, you need to ensure that that same labeling data is going to be used for every step thereafter in the pipeline. This also allows us to rerun steps in Airflow that may have failed because they're exposed in Airflow as individual steps. So when that processing fails, we can easily rerun it without having to start at the beginning. So another thing we needed to do is we needed the ability to run the exact same code that was written in development as we do in production. And by exact, I mean verbatim, no changes to the code whatsoever. The way we did that is traditionally a Spark task or a step in an ML pipeline would construct the path to write its data to. What we did is we moved that responsibility into this embedded library, and rather than constructing the path you write to, which might be environment specific for development, test, or production, you ask this embedded library for a path to write your data to. So now this library controls where the data is being read and written to, and it will provide you that path based on the context it's executing in. So if it's in development mode, you'll get a path to your development bucket or your development Hive schema. If it's in test, it knows about the test bucket, and et cetera. Additionally, in development mode, that path it gives you will be partitioned by your username, so you're not going to clobber anyone else's execution. Same as in test or production. What that allows us to do is we can run in the same environment that modeling code in parallel and have guarantees that they're not going to collide on each other's data. So any number of people could be developing this model code, executing it in the test environment at the same time, and they won't collide on the data. So we also needed to make the code observable at runtime or processing time. Again, on that embedded library, there's the ability to register custom metrics, such as model accuracy, number of users you scored, maybe average order value, any arbitrary metric that's important to this modeling use case. And then you can view those metrics over time as the execution is happening in production. You can add alarming conditions to those metrics as well. So if you developed a model with 30% accuracy and you want to be notified when the accuracy drops below 25% due to model drift or anything, I might still want to serve that model just to get the latest data and the latest labeling. But I want to be notified that I need to go and retune the model and resolve that model drift. So I would register a low urgency alert on that metric at, say, 20%. But I can also register high urgency alerts if the model accuracy drops below 10%. I want to ensure that model is not served in production, and I want to be notified to go and resolve that issue. So you just add metrics there, and at runtime, if those metrics are hit, you'd get a Slack message or an email or fire a PagerDuty alert, depending on the SLA for that particular model. So what this unlocked with the simplified pipeline, the metrics, and the I/O paths being controlled by this embedded library, data scientists can now develop their model, test in parallel, create pull requests of their modeling code, follow a traditional development practice on that modeling code, and bring it into production on their own without engaging an operations team. We can observe these models and what they're doing in production at runtime. We can generalize the CI/CD pipeline. So anything built on this framework inherits this free common CI/CD pipeline for deploying your code to production, executing it in Jenkins, creating pull requests and whatnot. All of that is free using these tools. We can also distribute any new tools or features into the modeling code with a simple version bump. So if we want to start generating a new type of report or enhance the alarming, we just need to simply update the version of this library and distribute it to any of the models that are using it. And more importantly, we don't need to coordinate with the operations team to make any changes to that modeling code. So some of the things we're working on now is improved SLA monitoring and job dependency. We need to define the SLAs that the modeling code will run under and kind of what the response time should be to address those failures in production. We need better idea of transitive job dependencies. You might depend on another Airflow job that depends on something else. If that root job either failed or didn't process, I need to know that there's an ETA to resolve that so that my job, the code I'm responsible for, is able to process and continue on. We're working on sending automated weekly reports of all of the metrics to the stakeholders. This would show the model metrics over time, how many failures there were, kind of the health of the model itself. We can capture things like cluster utilization. So if you had a step on a 40-node cluster that was only 2% utilized, it's easy to know that you could probably reduce that. Additionally, if the utilization was almost at the limits or memory was almost out, we can notify people to take a look at that code before it manifests in an actual failure. So that's kind of our journey to realizing DevOps and data science and some of the tools that we developed that empower that. And I'll run through a quick demo of it. It might give a better understanding of how this works. So for data scientists to bring this to production and to automate the pipeline, we had to make it as absolutely simple as possible. So we distribute a library into Databricks that's very similar to MLflow. And this library gives data scientists the ability to make their steps parameterless. Yeah, for sure. I meant to ask. So on the left here, this is the definition of a model. There's going to be 3 processing steps in this model. We're going to normalize some user data, normalize maybe orders domain of data, and then we're going to train a model. This isn't actually doing any data processing, just kind of showing the stub of it. So we're going to implement our normalize orders notebook. And similarly to MLflow, you start your step here. And in this case, it's the first step in the pipeline. We don't have any dependencies, so we say our dependencies are none. If we need to get the run date from the executor, we do that there. We can register and track our parameters. And in the hyperparameter tuning use case, these parameters are provided from that kind of hyperparameter tuning definition. And then here, we're going to ask this code for a path to write our data to. So we have a path, in this case S3, we're going to write the data to. We're going to label it as orders data, and that's all we need to know about that path. And then we do any arbitrary data processing. Anything you can do in Databricks, you can do within this platform. So we do our data processing, produce our data. Now we register the metrics, and we say this step is complete. So again, anything you can do in Databricks in the notebook here, you can do on this platform and inherit all of the free CI/CD, free pipeline, free monitoring, free metrics. So we'll go ahead and run that. So that executed, and when we asked the manager for this path, it gave me one specific to my users so that I'm not going to clobber anyone else's data. It also included this ID to provide a unique path. That way you never have to overwrite data, and your data becomes immutable, which can also lead to some reduced issues by having immutable data. And at the end, we publish this record to our API, which is essentially the meta information of this execution, including IO paths, metrics, parameters, and whatnot. So that goes to our central API. So we've implemented this step. We can run it locally. We're confident that this is the code I want to bring to production. We're going to do the same for the other steps. I'll show you the train model real quick. The only difference in this one is this step has dependencies. It's going to consume the data that was produced by normalized orders and normalized users. So we specify what it depends on. And that'll resolve that most recent execution we just did of normalized users and provide those outputs as inputs to this step. So we can also register parameters, create output data, but we can also get the inputs that were generated by that normalized orders execution. And we want the output path that was labeled orders data. So now that provides to us the S3 path that the normalized orders or normalized users step just wrote for its orders data. And now we can use that as in processing in this step. So the next thing we need to do is we implemented our notebook code. Presumably, we manually designed a cluster in Databricks that's capable of executing that step, whether it's a TensorFlow step or a Spark step. You might create a cluster, specify your instance types, specify your configuration. We need to capture that cluster representation to use that exact same cluster in our tester production runs. So the way we do that is we just attach to the cluster that we want to clone and that we want to use in our tester production runs. Just do a run all. And there we have this cluster that's capable of running our train model step. So we do that for all three steps, and we have a complete, code complete model ready to go to production. We showed it ran in development locally. It's using the manager, so we know it will provide accurate paths for production. We have our cluster. The only thing we need to do is implement the model pipeline. And this just tells the scheduler what the order is to execute these steps. So this is all the pipeline is now. There's 3 steps in this. So we say first run normalize orders and users in parallel. They have no dependencies, so the first steps in the pipeline. Then we can run the train model once these 2 are complete. So now that's our entire model step pipeline. If we want to bring this into Airflow as well, we just define some small Airflow configuration, what the schedule of it is, what the upstream jobs it needs to wait on are. And then when Jenkins goes and deploys this code into test production, it'll also create the Airflow pipeline for it. So that simplified the Airflow pipeline as well. So there's some utilities here. We could execute the whole model inline in Databricks. And the contract basically says if this model executes and validates in Databricks, it's good to go to production. The tooling has been validated to ensure the rest of it. As long as it executes here, you're good to go to production. So we have a Databricks notebook that would push this to Git. I won't show that right now. But what you end up with is you can push your code to Git, create pull requests, and with this common CI/CD pipeline, of course, you can do things like push your code to test production, execute the entire model within Jenkins, and if there's a corresponding PR for that build, we also post the results of that execution back into your pull request. So if you have a team of data scientists, you can now collaborate and review changes, see what the execution of that model was, see what the metrics and parameters were, and additionally, you can compare those metrics to a similar production execution. So if you made a execution that impacted your model, if you made a change that impacted your model accuracy, you can compare that metric from the exact same execution in production. That way you can validate some of your changes. And then additionally, when it's deployed to test or production, it will also push to Airflow. So this is what the Airflow pipeline that we defined here based on our model steps and our scheduler now pushed to Airflow and created this DAG that will execute the code on Databricks in the test or production environment. Let's see. I think that is kind of the bulk of the demo. I have 8 minutes left. Good time for questions, if anybody has questions. Thanks. Any questions? Maybe walk up to the microphone.
Hey. Thanks for the presentation, really good. We were trying something similar, and I would like to know if there is any pushback that you heard from the data science group in terms of the amount of DevOps that is getting transferred to the data science group,
right.
Or like how the support system is for the data scientist in order to go through this and so on.
Kind of the cultural changes that are necessary?
Yeah, essentially.
So in general, I think they're excited about it. They like being enabled to be successful at what they do. They like seeing their code brought into production. They like completing these projects. We do actually have 2 data scientists here, so they might be able to speak to it if that we've worked with if they want. But in general, it's been they've been happy to adopt it because they're empowered to be successful at what they do. We haven't transferred all of the alarming onto the data scientists yet. We need to kind of implement that SLA monitoring and ensure that the only errors they get are the errors from their code itself and not necessarily any tangential resource issues or anything like that.
Thank you for the talk. A question about the deployment model that you guys use is, I saw that you specified the dependencies on that file. Did you use that to create an image that you deploy then in production, or is that a specific target server that you have?
So that kind of transitions into the serving layer. So any one of these pipelines could be producing data, a Hive table, could be producing a servable image for a real-time model. But once that artifact is produced, it's kind of outside, it's into the serving layer at that point, and not necessarily inside this common data processing use case. We have code that will deploy that artifact into our serving layer, but this doesn't necessarily cover actually serving that model artifact itself. It's more in just producing the artifact, which is kind of what data science is responsible for anyways, is training that model, producing the artifact that could go into a serving layer, and often engineering teams would be responsible for actually serving that artifact itself. All right, any other questions? Nope.
So it seems like there's some overlap between this and ML flow and the new stuff that Matai announced this morning, ML workflow. Do you see a lot of overlap?
So there's a fair amount of overlap. These came out right about within 2 days of each other, actually. There was a couple requirements MLflow didn't meet for our organization in particular. I think MLflow will be the de facto standard for productionizing and doing DevOps and machine learning. But our two main requirements is we needed that common CI/CD pipeline, ability to push your code to Git, take it from Git, push it back into production. We needed that to be common against all of our machine learning models and all of the code base. Additionally, we needed to be able to run it in Airflow, to be able to rerun failed steps and be able to run steps in parallel. And before the 1.0 release, those weren't supported. So that was the reason we went with this path.
Okay. Well, I guess what I was asking is, if somebody wants to implement what you have implemented, they could do the same with MLflow.
The only distinction between this and MLflow is we do those dependency resolution. So the pipeline in MLflow is going to have kind of configuration and parameters and whatnot here. We moved all of that code into this library itself so that you don't have to maintain state and parameters in the pipeline. You can kind of pass information between the steps using this embedded library. That's one thing MLflow doesn't do. It would be trivial to implement it, but that one distinction kind of manifests in quite a lot of changes elsewhere in the automation.
Okay, thank you.
Mm-hmm.
Thanks for the talk. Other than the model generation and the CI/CD side of things, we also need to worry about the feature set selection and the feature serving and the feature engineering part of it.
Right.
Will you be able to touch upon how Nike handles this?
For sure. So that's going to be more on the data scientists or the people writing the ETL jobs. And you can create those features in engineering and whatnot still in Databricks. This is more the mechanism to do all of the CI/CD and automation and bringing that code into production itself. I don't know if that answered necessarily what.
Most of it, thanks. The one bit that I'm also interested in is feature validation. So once the model goes into production, and then if the data scientist wants to look at how the model behaved and what features were used for what instance at what time, does this pipeline also provide a way to access?
You can view the execution that it used, and there's an analysis steps that data scientists would write with it, so they know kind of what this model is doing that's in production, what the parameters were, what the input and output data was. But our models are generally executed on a daily basis to get the latest data, the latest labels for any new products. So it kind of just automatically runs behind the scenes.
Thank you.
Thanks. Cool.
If you have any more questions, I'm sure James will be happy to take them offline, and he'll be available in the back of the room. Please give a huge round of applause to James.
Cool. Thank you.